Kuzusangpo, Bhutan e-learning project welcomes children to this lesson. I'm Simadi Vichitri, teacher from Yangchinpu Higher Secondary School, and this lesson is for Key Stage 5, that is 11 and 12, and I'll be taking you through physics lesson on the topic Newton's law of gravitation and Kepler's laws of planetary motion. The lesson objectives are: describe Newton's law of gravitation, derive the equation of acceleration due to gravity on the Earth and the Moon, state and define Kepler's laws of planetary motion. Have you ever wondered what keeps the planets in its orbit? Or how is the Earth able to retain the atmosphere? It is able to retain due to the Earth's gravity, because Earth's gravity is strong enough to hold onto its atmosphere and also keep it from drifting into the space. The gravity or the gravitational force is a significant force which was discovered by Newton. And I'm sure you all are very much aware of the incident from which Newton started to discover the law. He observed the falling of an apple on the ground, and he reasoned out that it is because of the Earth's gravitational field. And also, Newton proposed that matter in itself is a source of force which will influence the dynamics of other matter. So anything that has mass will have the force of gravity. So can you guess if there is a force of attraction between you and the objects lying next to you, or between the objects? Yes, there is a force of attraction because it is a mass. Then, why is the moon that is revolving around the Earth not falling towards the Earth? So, we are going to reason out why. Okay, so Newton's law of gravitation basically deals with the force of attraction as stated earlier. Say like there are two spherical masses of m1 and m2 separated by distance r. So the force of attraction between two masses is inversely proportional to the square of their distance. The force of attraction is directly proportional to the product of the masses. So therefore, rearranging the equation and substituting proportionality sign with a constant, we have F is equal to G m1 m2 over r square, where G is the gravitational constant which has a value of 6.67 times 10 to the power negative 11 Newton meter square per kg square. Alright, so this is the main topic that we are going to talk about. We will be talking about the force of attraction between the mass of the Earth and the mass of the Moon separated by distance r. So the force of attraction between these two bodies are also given by F is equal to G me, where me is the mass of the Earth and mm is the mass of the Moon separated by distance r. So in case of formula, it is F is equal to G mem over r square. So before we really look into the value, we will have a look at the example. Say like we have the Earth and an object at a distance r. So in this case, does the apple fall towards the Earth, or does the Earth move towards the apple, or do both move to each other? The fact here is, as stated earlier, they both apply equal force of attraction because they are mass. But then, which one will accelerate more? So based on Newton's second law of motion, that is, we have F is equal to ma, and rearranging the equation, we get A is equal to F over m. And here, the relation states that if an object has more mass, it will have lesser acceleration. So therefore, since the mass of the earth is much larger than the mass of an apple, it is an apple that accelerates towards the earth. So similarly, now we'll look at the force of attraction between the mass of the earth and the moon. ME is the mass of the earth, M is the mass of an object, and RE is the distance. Here actually R represents the distance, but since here the distance is equal to the radius of the earth, we take the distance as RE. So the force of attraction between the earth and the object is given by F is equal to G MEM over RE square, and we know F is equal to mg. So here m is the mass of the object and g is the acceleration due to gravity. So cancelling mass on both sides, we have ge is equal to g me over re square. And here, as I stated earlier, ge is the acceleration due to gravity on the surface of the earth. So let's find out what is the value of acceleration due to gravity on the surface of the earth. So substituting the values, we have ge is equal to 6.67 times 10 to the power negative 11, which is a gravitational constant, and mass of the earth is 5.98 times 10 to the power 24 kg, divided by the radius of the earth is 6.38 times 10 to the power 6 meter. And calculating the value, we have ge, that is the gravitational force of gravity on the surface of the earth, as 9.8 meter per second square. So this is the value with which the earth pulls everything towards itself for the objects that are lying on the surface of the earth. So this is true only on the surface of the earth. Now similarly, let's find out the force of attraction on the surface of the moon. So for moon also, we have F is equal to G M over Rm square. So here mm represents the mass of the moon and m represents the mass of an object separated by distance Rm. So here Rm is the radius of the moon, and the above equation gives the relation between the force of attraction between the mass of the moon and the object. Similarly, substituting F with gm, so here gm is the acceleration due to gravity on the surface of the moon, which is equal to gmm over Rm square. So again, cancelling the masses on both the sides, we have gm, that is the acceleration due to gravity on the moon, which is equal to gmm over Rm square. Again, substituting the values, we have gm is equal to 6.67 times 10 to the power negative 11 times the mass of the moon is 7.35 times 10 to the power 22 kg, divided by the radius of the moon is 1.74 times 10 to the power 6 meter. So calculating the value, we have gm, that is the acceleration due to gravity on the surface of the moon, as 1.6 meter per second square. And again, this is true on the surface of the moon. Now, the conclusion we make here is all the objects closer to the surface of the earth accelerates towards the earth with the value of 9.8 meter per second square. Similarly, all the objects closer to the surface of the moon accelerate towards the moon with the value of 1.6 meter per second square. Now, we also have another formula to calculate the acceleration due to gravity on the surface of the moon, which is given by gm over ge, where gm represents the acceleration due to gravity on moon and ge is the acceleration due to gravity on the surface of the earth, equals to re over rm whole square times mm over me. So rearranging the equation, we have gm is equal to ge re over rm whole square times mm over me. Now putting the values, we have gm is equal to 9.8, that is the acceleration due to gravity on the surface of the earth, times the radius of the earth as 6.38 times 10 to the power 6 meter, divided by the radius of the moon as 1.74 times 10 to the power 6 meter whole square, times the mass of the moon 7.35 times 10 to the power 22 kg, divided by 5.98 times 10 to the power 24 kg. Now again with this formula also we get the same value, that is 1.6 meter per second square. So this is the acceleration due to gravity on the surface of the moon. Now again we have acceleration due to gravity on the earth as 9.8 meter per second square, and we know again now the acceleration due to gravity on the moon is 1.6 meter per second square. And in lower classes we learned that the value of gravity on the moon is 1/6 the value on the earth. Let's see if this is true. Yes, by substituting the values of the acceleration due to gravity on the earth and dividing it by 6, we get the value of gravity on moon as 1.6 meter per second square. Now the next thing is what force is required to keep the moon on its orbit revolving the earth. So this was the first this is related to the first slide that I have showed, that the moon revolves around the earth without being attracted towards the earth, unlike the falling of an apple. So what is that force that keeps the moon revolving around the earth? So let's go back to the equation again. We have gravitational constant, which is given by 6.67 times 10 to the power negative 11 Newton meter square per kg square, and mass of the earth as 5.98 times 10 to the power 24 kg, and mass of the moon as 7.35 times 10 to the power 22 kg, and the distance between the earth and the moon is given by r, which is equal to 385 times 10 to the power 6 meter. So this is the distance between the center of the earth and the center of the moon. Again with the formula F is equal to g m over r square, we are going to see what is the force of attraction between the mass of the earth and the moon separated by distance r. So putting in the values, we get F is equal to 1.98 times 10 to the power 20 Newton. So as stated earlier by Newton, that every mass has a force of attraction. So since the earth and the moon are mass, they attract each other with the force of 1.98 times 10 to the power 20 Newton. And also this is the same force that keeps the moon orbiting in and around earth. So this is the force which keeps the moon in its orbit. So now if this force was not there, if this force of attraction between the earth and the moon was not there, what will happen? The moon would have shoot out like an arrow. Now this is similar to the example we have seen earlier. Since the mass of the earth is much more larger than the mass of the apple, it is the apple that accelerates towards the earth. Similar to this, for the earth and the moon, me is the mass of the earth and is the mass of the moon, separated by distance r, and the force of attraction between them is F is equal to g m over r square, where r is the distance, the separation between them. So it is the moon that will accelerate towards the earth, because moon has lesser mass comparing to that of the earth, similar to that of an apple and the earth. But again, at what rate the moon will accelerate towards the earth? So here it is the moon. As we have seen already, it is the moon that accelerates towards the earth but with a different value of acceleration than that of the acceleration due to gravity on the surface of the earth. So that means the value with which the moon will accelerate towards the earth is different than the value with which the earth attracts the objects around the surface of the earth. So now let's look at the acceleration with which the moon accelerates towards the earth. So we have the formula F is equal to gmem over r square, and rearranging them we have F is equal to mm gme over r square, and substituting F is equal to mm times am, and substituting in the next equation we have mm times am equals to mm times gme over r square. So cancelling mm on both the sides, we have am is equal to gme over r square. So this is the acceleration imparted to the moon due to the earth's gravitational force. So this is the equation with which we can calculate the amount of acceleration imparted to the moon because of the earth. And we also know that G is equal to gme over r square. This is the acceleration due to gravity on the surface of the earth. Now dividing equation 4 by 5, we get am over g is equal to gme over r square times re square divided by gme, and cancelling gme we get am over g is equal to re over r whole square. So now here it means to say that the acceleration due to gravity depends on the separation between the earth and the moon, but does not depend on the mass of the moon. Similarly, even for the acceleration due to gravity on the surface of the earth, the acceleration due to gravity does not depend on the mass of an object. It only depends on the separation between the earth and the object. Now, moving on with this, let's substitute the values of the above equation. G is the gravitational, the acceleration due to gravity on the surface of the earth given by 9.8 meter per second square. Re is the radius of the earth, and r is the separation between the earth and the moon. And with the formula am is equal to g re over re over r whole square, and putting in the values we get am is equal to 9.8 times 6.371 times 10 to the power 6 divided by 384.4 times 10 to the power 6 whole square, and calculating we get the value of am as 0.0027 meter per second square. So this is the acceleration that is imparted to the moon because of the earth. Now, this is different from the force of attraction between the earth and the moon. So here, the force of attraction actually helps the moon to orbit around the earth, and the circular motion of the moon provides centrifugal force balancing the force of gravity between the earth and the moon, because of which the moon revolves around the earth without falling towards the earth. But here am is the acceleration that is imparted to the moon by the earth. And here, if for a while, if the moon stops, then what will happen? The force on the moon by the earth does not change. The force keeps on. The force exerted by the earth on the moon remains same, but only the balancing force is absent. So at this time, at this instant, when the moon stops for a while, the acceleration is given by force times mass. Now the next thing is the acceleration at that instant is given by force over mass. Now the next thing is, what will be the acceleration of the moon when it strikes the surface of the earth? That means the separation between the earth and the moon, which is given by r, becomes equal to the radius of the earth. So at that time, what will be the acceleration on the moon? So we know the formula, am is equal to g re over r whole square, and substituting the values, we get am as 9.8 meter per second square. So this is equal to the acceleration due to gravity on the surface of the earth. So since we have said that the acceleration on the surface of the earth is 9.8, and here also when the moon comes very close to the earth at a distance equal to radius of the earth, the acceleration imparted on the moon will also be equal to the acceleration due to gravity on the surface of the earth. Now, can you think what will happen to the object or even to the moon if it comes closer and closer to the center of the earth? What will happen to the acceleration if the object falls closer and closer to the center of the earth? Okay, now the final few things for this are the force of attraction between the two masses are given by the formula F is equal to G m1 m2 over r square. Ge is the acceleration due to gravity on the surface of the earth, which is given by G me over re square. Gm, it is the acceleration due to gravity on the moon, which is equal to G mm over rm square, which is equal to 1.6 meter per second square. And the last one is the acceleration imparted to the moon by the earth, which is given by am is equal to g re over r whole square, which is equal to 0.0027 meter per second square. So here from the first equation, we come to know that the force of attraction between the object depends on the mass and the distance of separation. That means what will be the force of attraction between the two masses also depends on their masses as well as the separation between them. Whereas in case of acceleration due to gravity, it does not depend on the mass of the object, but it only depends on the position of the object. Now with this we have come to the end of the first topic, that is Newton's law of gravitation. Now we will proceed with another topic, that is Kepler's laws of planetary motion. Kepler's laws of planetary motion basically deals with the motion of the planets. Actually it was a great astronomer, Tycho Brahe, who actually came up with the data to explain the planetary motion. But later it was his assistant Johannes Kepler who satisfactorily explained the planetary motion using the data recorded by Tycho Brahe, and later these laws were known as Kepler's laws of planetary motion. With this we will move on with the Kepler's first law. Kepler's first law is also called as the law of orbits. Every planet revolves around the Sun in an elliptical orbit, with the Sun situated at one of the foci of ellipse. And there are few terms related to the first law. The first term is called as heliocentric distance. It is the distance between the Sun and the planet anywhere in the orbit. Next we have perihelion and ephelion. Perihelion is the distance where the planet will be closest to the Sun, and at this point the planet will move with the fastest velocity. And ephelion is the point where the planet will be far away from the Sun, and at this point the planet will move with slowest velocity. Perihelion distance and ephelion distance. Now can you reason out why at perihelion the planet will have the fastest motion, and why at ephelion the planet will have the slowest motion? Now the next one is the Kepler's second law, which is also called as the law of orbits. It states that the aerial velocity of the planet orbiting the sun is constant, or the line joining the planet to the sun sweeps equal areas in equal intervals of time. It means that the planet covers equal areas in equal intervals of time wherever in the orbit. Now the last one, that is Kepler's third law, is also called as the law of periods. It states that the square of the time period of revolution of the planet orbiting the sun is directly proportional to the cube of semi-major axis of its elliptical orbit. So here it means to say that the square of the time period is directly proportional to the cube of semi-major axis, and from the diagram you can see that the distance between aphelion till perihelion is called as major axis, and half of that distance is called as semi-major axis. So this law means to say that how long will the planet take to revolve around the earth will depend, the time taken will depend on the semi-major axis. So larger the semi-major axis, more the time the planet takes to revolve around the earth. This is the reason why the planets closer to the earth, say like Mercury, takes lesser time to revolve because it has small or less semi-major axis, whereas the planet like Jupiter takes longer time to revolve because of the larger semi-major axis. So Kepler's third law is given by T square is directly proportional to A cube. With this, we have come to the end of our lesson, but before that, I have few assessment questions for you all. The first question is, a planet is orbiting around the sun in an elliptical orbit, at which point the planet will have the maximum and the minimum kinetic energy and why. The second one, at which point the planet will have the maximum and the minimum potential energy and why. Second question, describe the impact on the climate and weather pattern due to the different positions of the earth on the orbit. The last one is, what would happen if the earth revolved in circular orbit rather than the elliptical orbit? Thank you for attending this lesson. I'm sure you have understood something out of this lesson, and till then I'll see you in my next lesson. Thank you so much.